Assalamualaikum, we are from Group 5. Today we will present about frequency shift keying modulation and demodulation. Firstly, CLC clears the command window. Clear means remove all the variable from the workspace. Next, close all means close all the open figure. And the data we are presenting is 10001011. Now, let's set up our digital signal. We define the sampling frequency as Fs, the sampling period Ts, and the period of the signal T. S is the desired carrier frequency. Fs is the sampling frequency, 100 times the carrier frequency. Ts is the sampling period, and T is the period of the signal. Let's visualize our digital signal. We convert the binary information into the pulse train and then plot the digital signal. X data mean holds the pulse train for each binary bit. Next, the loop generates a sequence of 1 and zeros. T1 is the time vector for the digital signal. And finally, the plot visualizes the digital signal. Now, let's dive into frequency shift keying FSK modulation. We define two carrier signals corresponding to binary values 1 and 0. A is the amplitude of the carrier signals. BR is the bit rate. F1 and F2 are the carrier frequencies for binary values 0 and 1. Car-sig1 and Car-sig2 are the carrier signal. Now, we modulate our digital signal using FSK modulation. The resulting signal is a combination of the carrier signal based on the binary information. Mod sig represents the modulated signal. The loop modulates each bit according to the FSK scheme, and the plot shows the waveform of the modulated signal. Now, let's simulate the transmission over an AWGN channel. We add noise to our modulated signal. S and R is the signal to noise ratio. Rx is the received signal after passing through the AWGN channel, and the plot displays the received signal in the noisy channel. Let's proceed with demodulation. We extract the original binary information from the received signal by comparing it with the carrier frequencies. Demod sig stores the demodulated binary information. The loop performs demodulation for each chunk of the received signal. And lastly, the result is displayed as binary information at the receiver. Finally, let's visualize the demodulated signal. We convert the demodulated binary information into a pulse train. The loop generates a pulse train based on the demodulated binary information. The plot displays the received digital signal after the FSK demodulation. To complete the presentation, let's visualize the waveform of the demodulated signal. We construct the original signal based on the modulated binary information. The loop reconstructs the demodulated signal based on the original FSK modulation parameters. Lastly, the plot shows the waveform of the demodulated signal.
Next, I will explain about the block diagram and the Simulink of the FSK code. The FSK Simulink result consists of a block diagram that includes a pulse generator, two sine wave sources, a switch, and a scope. The pulse generator generates the 1 and 0 bit sequence, which are then fed into the switch. The switch selects between two sine wave sources that produce a specific amplitude and frequency. The selected sine wave is then modulated with the input signal using FSK modulation. The modulated signal is then displayed on the scope. Overall, this block diagram demonstrates the process of FSK modulation using Simulink. This one is the sine wave 1. The function for the sine wave block in the FSK Simulink block diagram is to generate two sinusoidal waveform with different frequencies. This one is pulse generation. Pulse generator. The function for the pulse generator block is used to create square wave pulse at regular intervals. This one is switch. The function for switch is block is passed through the first input or the third input based on the value of the second input. And this one is scope. The function scope in the block Simulink is a visualization tool that allows user to observe the output of a signal during simulation. Next, I will explain about the result in Simulink. I will now show you the Simulink model for FSK modulation and demodulation, which provides a visual representation of the process we've discussed. The model includes key blocks such as the data source, pulse shaping, sine wave, product band pass filter, and envelope detector, which are essential for simulating FSK modulation and demodulation. Simulink graphical interface allows for a clear and intuitive representation of this process, making it an invaluable tool for understanding and teaching digital communication concepts.
Okay, I'll be presenting a MATLAB code snippet that demonstrates quadrature amplitude modulation (QAM) and its subsequent demodulation with a focus on explaining each step in detail. So, let's begin with the initial section where we set up our simulation environment. Here, we are clearing any existing variables, figures, or command line outputs to ensure a clean slate for our simulation. Next, we define the parameters of our QAM system. These parameters include the carrier frequency Fc, sampling frequency Fs, and the frequencies of two message signals F1 and F2. Additionally, we set the signal-to-noise ratio SNR-dB to 20 dB. Now, let's generate the in-phase and quadrature signals. Here, T is a time vector ranging from 0 to the duration of the message signal. We create in-phase x1 and quadrature x2 signals using cosine function with different frequencies. Moving on to QAM modulation. The QAM signal S is generated by multiplying the in-phase signal with the cosine of the carrier frequency and the quadrature signal with the sine of the carrier frequency. So now let's introduce some noise to simulate a real-world scenario. We calculate the noise, power, and standard deviation, generate random noise samples, and add them to our QAM signal to simulate a noisy channel. Next, moving to QAM demodulation. We multiply the received signal Y by the carrier, in-phase cos, and quadrature sine components. Next, we design a simple FIR filter, a moving average filter for demodulation. The received signals are passed through the FIR filter, which aids in the demodulation. Lastly, we introduce a phase error in the demodulation and visualize its effect. A phase error is added to the in-phase signal and the filtered output is plotted to show the impact of phase errors in the demodulation process. So in summary, this MATLAB code simulates a QAM system, introduces noise, and demodulates the received signal using a simple FIR filter. It's a concise representation of a fundamental communication system with practical insights
with noise and phase error considerations.
Next, I will present about the plot diagram of QAM and its simulation result in Simulink. In a QAM, which is Quadrature Amplitude Modulation Simulink model, a random integer block, this one, generates digital data which is then passed through a general QAM modulator. This modulator combines two sine waves with the digital data to create a QAM signal. The signal is transmitted through a channel that may introduce noise and other impairments. On the receiving end, the general QAM demodulator extracts the information, producing a demodulated signal. The constellation diagram visualizes the QAM symbols in a complex plane, offering insights into the modulation scheme performance. Two sine waves and two products are involved in the modulation process, representing the in-phase and quadrature components. The sum block combines these components before the conversion from complex to real using the complex to real image block. Finally, the scope block displays the output, allowing a visual inspection of the signal and its characteristic. This comprehensive block diagram aids in understanding and analyzing the QAM modulation and demodulation process in a Simulink environment. To view the simulation results, we double-click the scope, and from the scope, the square wave likely represents binary information, which is on or off, or high or low, and the sine wave may carry additional information or modulation. Next is a constellation diagram. A constellation diagram is a graphical representation of the complex symbols in a signal, such as those produced by a QAM modulation. A constellation diagram typically represents the complex symbols of a modulated signal in a two-dimensional plane. The presence of four distinct points or stars in your constellation diagrams indicates that the modulation likely involved for QAM. In 4QAM, each symbol represents a combination of both in-phase and quadrature components. The 4 points on the constellation diagram correspond to the different combinations of amplitude and phase for these components. Each point represents a unique digital symbol. In conclusion, our presentation highlights the key aspects of FSK and QAM modulation techniques. By understanding these methods, we gain valuable insight into efficient data transmission and communication systems. As technology continues to evolve, the significance of FSK and QAM in shaping reliable and high-performance communication remains evident. That's all we can conclude from our Group 5. Thank you.